Emotion is something hard. It's actually not that easy to quantify in the numbers, right? Especially when we need to deal with some bureaucrats, for instance, in the tax office. It's always very hard to understand what kind of emotion they feel against myself. And for now, we want to ask the machine to understand the emotions, right? And how it can be done? Actually, that's why I call it hacking, because machine does not actually need to learn about physiology, it does not need to learn about psychological aspects of emotions. It actually takes the quantifiable data input. It actually could measure our heart rate, it could measure our breath, it could measure brain waves, and transform all of that into emotional signals. So let's start from the very beginning, why we actually need emotion recognition. So apparently, that's a huge market out there. So the reason for that is that we want our human-computer interfaces to be more personalized. We don't want to just interact with the machine, which is completely featureless in emotional sense. So one of the very good aspect is, for instance, this emotional robot which could interact with our children. So children actually will understand this robot as some being, which could react accordingly to how this child interacts with him. So that's a more important aspect. Another thing is, for instance, for business applications. So we could analyze emotions and use it, for instance, to get information how the customers react to some events in the business. How, in the retail applications, for instance, what emotions people feel when they search for some product in the shop. So all these could be assessed already now, and there are companies which actually measure biosignals and provide you with this biosignal, and then some people analyze this biosignal and try to figure out, okay, the person, when she looked on this particular product, her heart rate went up. Perhaps she was excited. But that's still a very hard topic. It's not really automated at the moment. And what we want to build, we actually want to build a machine which understands these emotions and could give us some useful information. But many people, perhaps there are people in this audience who actually will say that let's solve problems. So I have these applications on my phone which actually can trace my face, and from this face they can give me my emotions, for instance, if I'm smiling or if I'm grim. But apparently we know that emotions are disconnected from facial expressions. So it's not really the same thing. So person can smile but don't really feel happy, but also I can feel happy but I don't smile. So that's a very common situation, and we actually seen it also in our research. So that's why I want to say that don't trust that if the person shows some expression, that is particular emotion that the person feels, right? And so I don't think Angela was very neutral in this situation. So let's move forward. So what modalities then I should take? So one thing, as I said, facial biometry is important, but it's not the only signal that we can get. And another thing that we can focus on, we could focus on the context of the situation. We can analyze the speech of the person, we can use NLP techniques actually to get the sentiment of the speech and the context of the situation. We all have phones around us, so phones have speakers, not microphones, which actually can get the environment, right? So another thing that the same phones have accelerometers, so they can actually analyze the body language, how we move. And by using the phone, we already can say if the person is sleeping, or if the person is walking down the corridor, or if the person is sitting by the computer. So all this can already be traced. An important aspect which I will focus in this particular talk is these biosignals. So we already have a lot of different gadgets which actually have biosensors in it. So we could have these fitness trackers which actually have heart rate sensors, they have skin conductance sensors, we have very stylish and tiny EEG sensors which can measure our brain waves. And there are many, many more tiny variables which can all measure that. Of course, that's not a clinical kind of accuracy, but that's enough to say something. So let's proceed. We actually need all this data. We need facial biometry to say something. We need body language. We need biosignals. And we need then to fuse all this. So in this respect, we will measure the context, and then somewhere here in the cross-section, we actually will find the right emotion. And when I talk about different biosignals, so this emotion recognition is not a new topic. So it seems very exotic for this community, but it's not really new. People worked on that for a very long time, and there are the books published on how to measure emotions from different biosignals. There are dozens of PhD theses that I have read, and which deal with different signals and how to measure emotion from these signals. But apparently, there are not so many solutions on the market. So if you look for sleep trackers, there are already quite a lot of sleep trackers, but they don't really measure the emotions. And that's something that could be done. So, but why it is not done yet? Because there are a lot of challenges. And one of the main challenges, and it's very important for this particular conference, this is a data science conference, and there is no data. So actually, there could be some data, but it's very tiny data set. These are very tiny data sets, and they are almost not of the commercial quality. And the first thing that you need to deal with, you need to actually find the data, collect it, and then analyze it. So that's the first thing. Another thing that I already mentioned at the very beginning, so emotions are a very hard topic, so it's actually not that easy for many people to understand their own emotions, which we've learned from our experiments. We actually find out that a lot of people are emotionally stupid. And I will tell about some completely hilarious examples of that. So people just cannot really even put the proper label for what they are feeling. So that's why the data set at the end will be very noisy. So, but when you have a noisy data set, for instance, in computer vision, you can just put an expert nearby, and that expert will look on the image and say, okay, that's this particular class. That does not really work here, because this data is kind of featureless. So you look on the data, and you cannot really say from the data if the person was happy or if the person was angry. So you cannot really put the expert nearby. And apparently there are some effects of central neural system. If the person is thinking about what kind of emotions she feels, apparently the emotion is not manifested in the biosignal anymore. So that's also important. And at the very end, there is no accepted theory. So there are some theories which deal with emotions, but there are not so many. And we deal with, in our research, we use so-called discrete emotional theory. So there is a theory by Paul Ekman, and he said that there are like 6 basic types of emotions, which are anger, fear, contempt, sadness, and happiness. Maybe I forgot. Yeah, I told about everything. So, and based on these 6 types, we can build like more complex emotions. And there is a very good visualization of that. So we can build a 2-dimensional diagram. On one side, we have a valence of emotion. Is it positive or negative? And on another side, we have arousal, so how excited the person is. And if the person is very relaxed, it's here. And it can be either relaxed or sad, or people could be very aroused, and it could be anger or joy, right? And you could put other emotions in these squares. So that's how we actually quantify that. So the first thing that we need to figure out is the context. So that's easy. So that's, as I say, there are already techniques which allow you to do that. So I kind of skip this. And I also skip the face recognition. It's basically done. So I don't focus on that. But I will focus on biosignals. So first, the heart. So it's long been known that the heart is kind of reflecting our emotions. And we have a lot of heart sensors out there. So we have these fitness trackers. We have this very tiny, compact ECG trackers, which could track directly the electrocardiogram from the heart. And there are even new types of sensors. For instance, MIT developed a sensor which is environment sensor, and without anything on the body, it can actually sense what is the heart rate of the person. It's done by this very tiny micro motions of our skin. So, and this micro motions actually could be captured by reflected radio frequencies. So once we have the heart rate, it will look something like this. So we have some fluctuations of the heart rate. The heart rate is how often our heart beats per minute, and it somehow fluctuates. And there is a very naive picture of this. I think it's very naive because it doesn't really work in this way. So that if the person is very relaxed, then there is this very visible sinusoid. But when the person is very stressed, it's kind of like this, very stochastic. And then if you do Fourier transform on top of that, you actually can see it in the power spectrum. But now, we tried this approach, and I could say that I never seen something like this. So I've seen mostly pictures like this, stochastic, and that's why I more support this view on the heart rate as some stochastic time series, which encodes some information, and you need to use theory of stochastic processes and nonlinear time series to actually extract this information. And suppose you have the stochastic series, and there was some stimuli, you tried to frighten the person. If you look on the series itself, that's why I say that it's featureless, it's just the same on the left and on the right. But you know that there was some information, right? So you can construct features which were described, for instance, in this paper, which allow you to discriminate between different correlations within the signal. So that's approach that I used in my research. Another signal, which is very old one, it's a skin conductance. So we have 2 electrodes on the skin, and it measures how sweaty we are, how much the skin conducts. And apparently people use it for a very, very long time. It's very popular in Ukraine. But in some countries, people consider it as a pseudoscience, the polygraph. So when we want to measure if the person is lying, so the polygraph is that method. It actually uses skin conductance to say how much the person is aroused or not. And it's in the experiment. Now we can use these cheap research sensors, which basically are on our fingers. But in the nice devices, in consumer devices, they look very stylish and could just fit into any of the smartwatches. And almost any smartwatch has these sensors. So the signal itself will look like this. So when the person is aroused, we will see peaks in the conductance of the skin. And these peaks could be very easily counted, how many of these peaks I had during some period of time, and that will be the feature. And this feature will discriminate how much person is aroused or not. So I said that there are these 2 axes. One is how much the person is aroused, and another axis is the valence of the emotion, right? So this will allow to discriminate the arousal only. So now let's move to the brain waves. The brain waves, as I said, there are a lot of sensors. So this looks like a stylish sensor, but there are even more stylish. So these are the EEG, electroencephalogram sensors, which measure actually the same electrical activity of our brain as the heart rate sensor measures ECG. And at the end, we will have kind of a power spectrum of this signal, and we can split it into the frequencies, and these frequencies will have different spatial activity in our head for different kind of emotion. So that's how we can actually differentiate now the valence of the emotion. Is it positive or negative? And in our lab, we actually did not use the raw signals itself. Apparently, this technology is quite well developed already, and one can buy the ready consumer products, which allows you to differentiate arousal, and currently it does not differentiate the valence, but we use it as a control device. So we put it on the person's head, we measured heart rate and skin conductance, and this device was like a control thing if there is indeed was some emotion, because people are emotionally stupid, they don't mark correctly. So now we have these sensors, and we want, so as I said, we can qualify how much they contribute to either valence or arousal. So from my own experience, I see that the heart rate can really allow you to say if the person is very calm or if the person is stressed. So we already can build devices which will detect the stress. Also, the brain activity is very good in that, so you really can even trace how much the person is focused on some subject, if he is reading or if he is driving the car. Then the skin conductance is also a very good indicator of how much the person is stressed, but it's less informative than the heart rate and the brain activity. Why I say so? Because all these consumer devices, they're very fragile to motion. So if I will do like this, so this sensor will be completely ruined, so the information will be completely lost. So then the facial expressions, they kind of give you the arousal, but it could be completely not true. And the voice expressions can also give you some information. Now, what about the valence? As I said, some of the signals contribute to valence, some of them not. It's very hard, actually, to say if heart rate contributes to valence. It contributes a little bit. Then the brain activity already actually gives you if the person is positive or negative mood. The sweatiness does not give you this information. And then finally, the facial expressions could give you if the person is meant positive or negative. So having that, we need to do the signal fusion. We then do this basically moving window approach and qualify what was the emotional signal for every second of our measurements. So these are basically different signals, either electrodermal, respiration, how much person breathes, and the heart rate itself. So I did not notice at the very beginning, so actually our research is very much under NDA. So I really can talk about more like literature overview and my own experience, but I cannot really show you our own results here, but fortunately, there is a lot of research literature that I can share with you. So now, the very important aspect is how to get this data. And that's another huge part of this. So first thing is that we can actually start recording from the single subject. We can put all these devices on the person, put some emotional stimuli, and record that in the parallel. But the thing is that actually that does not really work for mass recording, because then you will spend like years of collecting some reasonable amount of data, and that does not really work in commercial applications. So what we do, we actually do this mass recording. So we had a group of people of around like 20, 30 people. We put a lot of sensors on them, and we recorded them in parallel, giving them some similar stimuli. And then there were experts who actually were looking on the video of these people and tried to figure out what emotion they felt. And another question is how to induce emotions. Do we induce all emotion in one session, or we actually give person some long clip and allow the person to be in one context? So that's actually very tricky question, because in this case, the first one, in this case, you kind of switch between different emotions, and that does not really happen in real life. So it maybe happens for small children, but it does not really happen for adults. And for this case, we find it more realistic. But then the problem is how the people actually mark these yellow lines. So what are the labels when the person really felt the emotion? And apparently people don't really mark that well. So that's really a problem. And here is one hilarious story. So we watched with these people, focus group, a comedy movie. So it was some Friends or something like that. So it was like pure comedy without anything special. And Actually, one person marked all kinds of emotions. So it was anger, it was fear, it was sadness. It was almost, so the person sometimes felt like if you look on these marks, it's like she was completely desperate. But the thing is that this person was just kind of reflecting of the context of the movie instead of like feeling her own emotions. So that's why we needed this additional EEG device, which actually gave the information if that was true label or not. Or you can just filter out all the labels which do not fit the context of the session. So that's why there is no real ground truth for this data. So if you look on the self-labeling accuracy, at the end the accuracy is around 70%. It's actually good enough because when we build this device, it feels really, really nice, and you really feel this feedback, but actually it's very hard to argue it with the business, like if this accuracy is high enough or not. Which? You mean here? Ah, okay. High arousal, high valence, low arousal, high valence. So these are, okay, I needed to describe it more detail. So it's from the DCAF data set, so they did the same experiment. So they had data of a stimuli which was marked particularly what kind of emotion it should stimulate. But then, and then they kind of evaluated it on a group of people, but then they gave it to a different group of people. And apparently these people put it in completely different context. So for instance, this red dots should be actually in this quadrant, but they sometimes go here. Black ones should be only here, but they go often here, and so on. So they mix them. So people just mark arbitrarily. So that's a problem. So now when we can build the system will be the next. So we have all these bias signals. We first discover the context of the session. Then we can measure the valence and the arousal by fusing all these bias signals. And finally, we get some emotional, discrete emotion for a particular situation. And why it's interesting? Because now, when we have emotion, we can build so-called feedback loops. We can affect the person back, and actually to stimulate the right experience of the person. So that was in the recent Blade Runner. We've seen this one of the main characters who were the robot who actually said what our main character actually wanted. So imagine you have an environment which actually feels your emotion and can adapt to your needs. So to dim a little bit the light or to turn on the right music. So that's what we actually willing to build here. So in this sense, we have sensing, we then have emotion recognition system, and then we go all the way back to the person and we affect the person. So that's called effective computing. So let me summarize now. So the take-home message is the next. Emotion recognition is already here. So it's not that widespread, but it will appear in more applications right now, and we can already use it in business. But it's still a very hard problem, so there are still challenges to overcome. It allows for this new engaging applications. So one of the really killing applications, I could say, it's when you go to supermarket and you don't come out of the supermarket with this disappointment that you didn't find the right product. So you can build the advertisement system which actually will act on yourself and actually induce the right emotions. So you could help to find the right product. And if you want to develop something here, it's kind of a vertical AI solution. So you really need all the different kinds of technologies here. So you need facial recognition, you need sensor fusion, you need development of the new sensor, you need to collect data yourself, and you need to analyze all this data with time series analysis and so on. So with this, I very thank you all for the attention, and so let's go for questions. Thank you.
It was a very interesting speech. My question is, what is your opinion on where we can actually take those data sets to, I don't know, somehow advance the technology in regards to recognition of human emotion? Because as you've said, people are emotionally stupid, and how can we overcome this?
Well, as I said, there are ways to design the experiment. That's the first thing. So you really need to perhaps invite several experts who will and record the video of a person, record the EEG, and actually analyze. The next expert could see all the available data and then give the assessment if this labeling was correct or not. I actually also say that it's better not to allow persons to label by themselves at all. The reason is that when we think about our emotions, we actually block it. So once we think about that we are happy, it's actually not manifested by our biosignals. We found it also experimentally. So in our next experiments, we actually don't do that. So we have external experts who watch all the available data, the visual data, the EEG, and all the sensors data, and then make the decision if the person was really affected by something or not. Yeah, that's very important, actually. The people have to think that they are not monitored. Right?
Thank you so much for the talk. It was fascinating. And it's a really cool insight that people tag what they see in the movie, not their own emotions. I guess every field has their own problems with annotation, and this wasn't an obvious one. You know? And my question is whether you think this automatic detection of emotion could replace human therapists sometime in the future.
Yes, that's exactly what we are thinking about. So that's one of the main applications in the healthcare, as you could say. So-called engaging. So there is engaging retail and empathic medicine or empathic healthcare. So we know that there is a problem that all people cannot really have attention of a doctor. That's why we will have doctors being replaced by the computers and AI. So we want this AI to be actually empathic. So that's where emotion recognition will play an important role.
Thank you. Really great talk. I have one question. So all this research, all this data is based on proposition that humans only feel like one emotion at a time. But isn't this like oversimplification? Was there any attempt to attack this problem as a multi-label problem? Because like people often feel multiple emotions at the same time.
That's the right problem. When we actually ask people to assess their emotions, we had multiple labels. And that's allow you to, so let's say, look on this plot. So that's one of the experimental plots from one of the papers. So you see it's very messy. So then the person was putting different labels. So they will constitute different points in this plot. And then you can do like weighted averaging or something like that. Right. There's the question out there.
Thanks for great presentation. I have a question about the production ready state of that. So what is the latency or minimal period for detecting some of the emotions? Another question is about how much is the success rate? And the other thing which is still interesting, how could you purify the analyzation? Like you have some data set and some, I don't know, learning stuff by people tagging themselves, like it was pleasure, sadness, or anger, or another thing. So what are the methods for simplifying or better refining the results? Thank you.
Okay, let's start from the beginning. Can you
latency or
latency? Okay, there is real time. It's now working in real time. So it's actually not that complicated from the machine learning part, so you don't really need these deep neural networks which don't work in real time, so it works well. And so then how to purify data?
What is the minimal period to detect some emotion?
It's really real time. It's less than seconds.
No. To analyze.
You mean to analyze the data? Okay.
Yeah,
so then you need around 1 minute of the moving window. So there are like empirical studies which say that the motion lasts from 10 seconds to 1 minute at most. So that's why you actually can detect that. So Another question was
About success rates.
success rate. So as I said, the human error is around 70%. So not error, but human accuracy. That's why you cannot really jump much above that. So there are a lot of papers who claim that they have success rate of above 90%. I very much doubt that. So when I looked on the data sets, they have very tiny data sets. It's more likely to be overfitting. Right.
Okay, and the latest thing about like purifying the resultation after the data set's being processed.
Well, you can build some hidden chain Markov model, for instance. So it's really possible to do that. So currently we really analyze one moving window at a time, but you can complicate your problem more and more and make it more expressible. So.
Okay, thank you.
So.
May I ask, thank you for a great speech, very inspiring. May I ask a more high-level question? You have mentioned application in medicine, healthcare, and advertising. Are there similar requests from requests for this research from other types of businesses? And also, if you can mention few real use cases, maybe not from your NDA work, but from other companies, it would be great. Thank you.
Well, as I said, that's engage in retail. So that's the first thing. Also healthcare. Then automotive. We all will use self-driving cars. We want the self-driving car to be like a horse, actually, to feel us. So that's where it could be used already now. We can also assess the stress level of the truck drivers already now. So that's what our group does. So we created this wheel which measures the cardiogram and you can feel the stress. And it's any kind of market research as well works here because you want, if you do market research, you want to understand what was the emotional feedback there. Also smart houses, or that, all that. For market research, that's exactly what I was showing actually here. So there was particular case, so this one, that's iMotions, they actually do this market research. So, I mean, they have application for market research. They don't recognize emotions so far, they don't only record the bias signal, but they have this wonderful platform which actually allows you to synchronize different bias signals. And there was one question, I think, Oles. Okay.
You mentioned that it is hard to get a data set because people don't recognize emotion correctly. What if we go another way? We measure when we're actually sure that person now is some state. We're sure about that, and then we measure their physical parameters. For example, we can use some drugs maybe, or another situation when we're really sure that, for example, this drug make a human feel this way, and then measure their physical parameters. Of course, we should exclude maybe side effects of drugs, and
but
then we'll work this way.
Kind of, there are a lot of ethical questions. If that's possible, then how much massive data set you can build out of that? I mean, you can kill the person by actually.
I maybe don't mean illegal drugs, but some preparators we can still use.
Yeah, it's hard. It's already hard actually with video stimuli, really. So it takes a lot of time. And
we have one more question, and please be strict and clear and short, okay? Because every question is like.
Thank you for the great speech.
Like a speech.
Question: do you use many types of data based on sensor grounded on the body, hand-mounted sensors, and so on? And is there some pipeline of minimizing type of count of data you need to predict particular emotions. So we can use this data to make predictive model of human emotion system, but I think in real cases you typically have a visual stimuli and maximum audio stimuli, and human can co-feel some emotion and make empathy based only on visual and audio stimuli from person you have a conversation or something else. So is there some pipeline how you can minimize type of data you need to predict emotion based on extended this big crowdsourced data set of different type of sensors?
You mean while doing the experiment, or actually in the real world when I already used the device? So let me speak quickly. So the thing is that actually you can start from the one single measurement from, like, let's say only GSR, only the skin conductance, and already predict how much the person is stressed. The only reason is that why I propose to use more sensors is actually to increase the accuracy. And so you can combine it with heart rate, and that already will be high accuracy. But the reason is that sometimes person can feel emotion, but it does not really go all the way to the physiological signals. So then it will not be visible from the heart rate and GSR. So that's why you need to add additional input. You can really start from the single sensors, like single wristband. So that will be already enough. Or instead of the wristband, if you want better accuracy, you can have an ear clip, so it also should work well. But if you have a phone which actually record all this emotional activity, then it's worth of using a gyroscope to actually find out what was the context, what was the body motion in that period, and so on and so forth. So as much available sensors you use, the better, but you can go all the way down to a single sensor.
Thank you.
You're welcome.
So guys, any questions?
Thanks a lot.
Let me remind you that the best question will get some surprise.
So first of all, thank you about this great speech. This is very interesting area of research. And I have maybe a small question, and it's a little bit of philosophy. Okay, so I will try. We all know that there are two main reasons for doing innovations and research in the world. It's either war or business. And as for me, the main thing in this area is the understanding why people do some choices on business area, like why they are buying some products against another. And I'd like to ask you about as a researcher who doing this many years, as I understood, have you ever thought about maybe should we do any research in this way? Because as for me, it scares me. It leads for the ruling people, like doing them slaves of marketing.
In some sense, yes, but also it drives a lot of other areas where you can have positive innovations. Like, as I said, you can have these automotive innovations in the self-driving cars. So that you will have a closed environment, and you really want the environment to be kind of responding to your state. And if somehow I can find a solution which will make me less depressed, I also will be happy. So, and again, like these retail applications, they actually are targeted in the way that they make people more happy. So I think it's important.
It's a really very, very tiny border between...
Yeah, but there is a tiny border, that's true.
Thank you.
Thank you.
Well, thank you. We are out of time. So the best question was the best question?
It's kind of, there were so many questions. Sorry, guys. I think I really remember this question of the gentleman there. So he asked this question about how, so that we don't really have this perfect discrete model. We can have this very kind of mixed emotions. So I think that was a tricky question. And good
so
one.
the present goes there.